All right, I guess that's working. Doesn't give me a very good signal, but yeah, okay, so that's on. All right, so I'm taping currently, and so I did manage to get the the recording from the last lecture posted to Blackboard. The link, it's actually a YouTube video, but but the link is posted on Blackboard, and also the link to the class notes are also from last time, also posted on Blackboard. But I had a little mistake in Blackboard. There was a little quirk in Blackboard that I didn't understand. So the access was blocked to those two things until yesterday. And then someone, was it Lewis? Someone told me that the access was blocked, and so it took me a little while to figure out what was going on, but I managed to get it unblocked. So you should have, if you want to, you can go back and look at the class notes from last time. We're going to use those again today for part of the lecture because we're not through with those notes. And then you can review the whatever parts of the class video that you feel like you might want to review if that's necessary. And so hopefully that will be there every time. You know, it takes me a few hours to get that processed and uploaded, but hopefully within a day after a class, I'll get that link posted on Blackboard. So if you do miss class, and I hope you won't miss very often, but if you do have to miss class, then you can refer to the video that will be on the Blackboard link. Okay. All right. So I did, as I mentioned here just before class, but before some of y'all logged on, here is the, if you can see through all of these windows, here's the main page in WebAssign, right? And so these are the 3 homework assignments that I currently have posted. And so, we're up to almost everyone now. So that's really great attendance. We may be missing one person only. So that's terrific. So I hope we can continue the really good attendance through the semester. So there are 3 assignments now. Remember, this easy one is just entering answers in WebAssign, and that one, a lot of people have already worked on that. I saw there were lots of 100, so maybe that's not too hard, although there might be 1 or 2 odd questions in there in trying to learn how to use the gadgets in WebAssign, not all of which we will ever actually use in the class. This is just a generic assignment that comes from WebAssign. I didn't create this assignment. So this is just a generic assignment. And then, but the first real assignment with any math content is this algebra review. This is kind of long. So this is a little bit longer than most of our assignments will be. This is 25 questions, although a lot of the questions are short, or they should be pretty easy to do. And because it's all just review for you of your algebra skills, so that you know, you won't you'll get a little practice with your algebra before we get to, you know, something like a test, so you don't be making hopefully you won't be making unnecessary algebra mistakes on a test. You don't want to lose points you know, because of you know, your algebra skills being rusty. If you're going to lose points, you want to lose them on the calculus part, right? The new part, not on the algebra part on a test. So so that review is that's our first real meaty homework assignment. I have that due as Thursday, a week from today, but we'll talk about that next week. And if we need to add time to that, we can, because again, it is 25 questions. So it's you know, a little bit lengthier than most assignments. This new assignment that I posted is due the following week, or at least that's the due date that I've got on it. This is stuff that we will start talking about today. This is only 9 questions, so that would be a would typically like to have homework assignments less than 20 questions. So, and I think that's usually the case. So don't get freaked out when you see this long algebra review. That's a little bit longer than normal. Okay. I will open the algebra review here just for fun, just to see what that looks like. But do y'all have any particular questions that you want to ask me at the moment? So it doesn't have to be about WebAssign, but just about the course in general, or is there anything that you're having issues with so far? Everyone is okay? All right.
Oh,
Yes.
I had noticed when doing the first homework, I had finished it last night, that you have multiple attempts on. I had multiple attempts on each question. Is that how it's going to be for all of the homeworks, or?
Yeah, that's a good. I'm glad you asked that question because I forgot to mention that. Yes, you will have multiple attempts on every question. Um, so I think for most of the homework assignments, it's set to 5. So you've got 5 attempts per question. So if you want to burn up a couple of attempts, just experimenting while you're sort of getting used to the question, that's fine. But when you get closer to the 5th attempt, you're gonna have to be more careful about what you're doing on the problem. And once you've run past the 5th attempt, then it's really hard for me to add attempts. So try to make sure you know what you're doing before you get to the 5th attempt. So that being the case, if you get, say, past the 3rd attempt, and you're really confused about either how to do the problem, you just don't know how to do the problem, or you think you're doing the problem correctly, but for some reason WebAssign is not accepting your answer, which it does frequently, then you can email me, right? There's, with each question, I think it's either ask your teacher or ask your instructor. So click that link and say, ask me whatever question you want to ask me, right? I think I'm doing this right, but it won't accept my answer, or I don't know what I'm doing here, right? Whatever the nature of the problem is, email that to me, and I can see the question and your response, the last response that you put in. And so many times just through email, I can answer the question. Sometimes the questions are a little bit harder, though. It's hard to answer an email, right? Because you're just typing. So I might say, we'll talk about this in the next class, because I'm not going to be able to answer this properly via email. Okay. So it's usually 5 attempts. For some of the homework questions, some of the homework assignments, I think I upped it to 7 attempts because some of them are a little bit trickier than others. I don't know what it's set to on the algebra view. I just looked at the functions and graphs this new assignment. I think that one was set to 5. So yeah, that's how that works. And let me tell you, the most frustrating things for students is WebAssign is it's a computer system, right? And it's the computer that's grading you, and the computer algebra system that powers WebAssign is quite good, but it's not always perfect. So it will sometimes expect you to have an answer in a particular form, and your answer may be correct, but not in the form that WebAssign is it will accept, and that can be frustrating for students. So that's why I say email me, and I can look at your answer and tell you, oh, that answer is correct, but you need to type it in like this, or tell you, oh, you're off by a little bit here and there. Another thing that you want to be careful about in WebAssign, and so once you've gotten a few of these questions, you'll remember this. But if WebAssign does not say enter 3 decimals or 4 decimals or however many decimals it may indicate on a problem, that means WebAssign wants the answer in exact form. So it does not want it in decimal form. So for instance, if the answer to a problem is square root of 2, and WebAssign does not say, use 2 decimal places, then you would actually have to physically enter square root of 2, right? So using the math palette, you would, create the square root symbol and then put a 2 under it, right? Okay. But if WebAssign says, use 3 decimal places, then you would give a decimal approximation, right? So does everyone understand that? So you have to kind of look kind of carefully at the instructions. If it doesn't say, give decimal approximation, then it probably wants the answer in exact form. So that might involve square roots, or it might involve fractions, right? Okay. So and again, you can create those using the math palette. Okay. So good question there. So everything I said there was kind of a lot. So, with a few homework assignments under your belt, you'll become familiar with all these things that I just told you. Are there other questions there like that one about anything so far?
I have a question. Will
Uh-huh.
we be using lockdown browser?
You do not need to use a lockdown browser, no. Any browser will do. I think Chrome works really well with WebAssign. I'm not sure how Edge works. I haven't tried Edge that much, but yeah, you don't need to use a lockdown browser. Is that what you asked, Calvin?
Yeah. Like, we're gonna need the lockdown browser at all this semester?
No, you don't need a lockdown browser. No, not locking anything down. We're free as a bird here in calculus. So no lockdown browsers. I don't think, not sure how good WebAssign works with the lockdown browser anyway. So, but anyway, we don't need that. The only time you would, we would want to use a lockdown browser is with, on taking tests, but we're not going to take tests in WebAssign. Those are going to be, handwritten tests, right? Okay, that you will, that I will post, and you will email me back your written responses, right? So, yeah, so we don't need a lockdown browser. Now, you may have asked the question about lockdown browsers, though. That does bring up another important issue in WebAssign, and that is, but this is just a general, it's not about WebAssign. This is just a math question in general, right? There are lots of programs, of course, on the web that can do calculus for you, right? Okay, and they can do symbolic calculus as well, not just numerical calculus. They can manipulate symbols, right? They can manipulate variables and carry out most of the operations that we have to do in calculus. All right, so and there are also, of course, lots of great videos on the web explaining, how to do things in calculus and other math topics. All right, so and those things are great. And I'm not telling you to not use them. In fact, we are going to occasionally here in the class use software, and I will demonstrate that in the class, right? And I will actually encourage you at times to use that, particularly graphing software. So if you have a graphing calculator, I will encourage you to use that when it's appropriate. But do not get addicted, right, to these tools. So try to avoid using external math programs to help you do calculus, except possibly for graphing. Try to avoid using those, right? Also on the homework, there's lots of course, all the programs have lots of help, right? And they have videos that go along with the questions. Some of those videos are better than others. You will see when you look at the videos, and I definitely encourage you to look at the videos when you need them. And the other help features in the homework when you need them, right? You paid for that, and they are beneficial. But again, you don't want to use those as a crutch, right? So you definitely want to try to do the work on your own and use the help features as a last resort, okay? Because on the tests, even though the tests are, they're take-home tests, right? I'm going to be asking you conceptual type questions on the test that you will not be able to find help with anywhere, okay? So you need to, for your own benefit, right? Not only with your grade, but for your future performance in math courses, right? Do your own work, right? Okay. So you'll know what's kosher and what's not kosher, right? I don't need to tell you those sorts of things. So that's just my general warning. I'll try to repeat that through the semester, but since we're starting your homework, now's a good time to say it. Okay. So, all right. I see Madison. Madison, are you there? You want to say anything?
Hello. Yes, I'm here. Good morning, guys. I hope you're doing well. So, yes, I exist. I'm your virtual SI this semester. Thank you, Professor. I'm still trying to figure out when I'm going to be having those sessions. I did post my info in the on the Blackboard page. If you look to the left with all those tabs, you'll see SI Leader Madison. If you look in there, you'll see all my information. You'll see my introduction video. You'll see a link to more SI information if you guys have any questions. We do more than just math. We do a bunch of other subjects as well. So hopefully you come by to check out my little thing. Be sure if you're interested in SI sessions, if you are needing any help with any homework, if you want that extra practice, I'm here for you. Please go to the survey and select a time slot that works best for you. So I hope you guys take a look at that. It'd be super awesome. So yeah.
Okay. All right. So, oh, Madison, I did add you to the WebAssign. So if you log on to WebAssign, this course should be there under your list of courses. So,
okay.
I just put
with my Gator mail, I guess, or
I'll well, you already existed in WebAssign, so it already knows you have a username and a password. So you may have to try to recover what those were if you don't recall. But you're in the system, so I just added you to my course. So
awesome. Okay.
All right, so you should be able to, if you can log on, you should be able to. It's probably just your Gator mail, yeah. But if you can log on, you should be able to look at the course currently. Okay. Well, I don't think I'm going to open one of the homeworks now. So unless there's just specific questions about how to go through particular problems, right? Okay. So I think almost everyone, or at least 20 people, I think this morning were already enrolled in the course. So remember to do that right quickly, so that you have a 2-week grace period before you have to actually pay to register for the course. You can still enroll in the course and do homework. So so there's no reason not to get onto WebAssign. Let's see. Here's the Blackboard page, and remember, right here is the class notes and videos, right? So if you click on that, it should take us to, there's the link to the video lecture for last time. There's the link to the class notes. If you're still confused about the instructions for getting onto WebAssign, just go to the syllabus. So there's the link to the class syllabus, and scroll down to maybe the 3rd page or something, and it will have the instructions for how to enroll in the class in WebAssign, right? All you have to know is that code that's given in the syllabus, and follow the instructions at the WebAssign website, which is also given in the syllabus, and you'll be able to get enrolled in the class, and then ultimately register, right, when our 2-week grace period ends. Okay. All right. So one other thing, remember, on the Blackboard page, eventually we'll have sample tests there on the Blackboard page, but we're not near ready for a test yet. And then that's where I'll be posting the actual test for you to do and the answers. But again, we're a long way away from that. So other than announcements, these are the main things you'll be looking to the Blackboard page for. Okay, are those things. Let me close that. Tab. And would we have a question there? And
yes.
Yes.
How after the class is done, how long do you put the video in the notes, just so I know when to expect them?
The notes can usually get posted really quickly because that's easy to post, but the video, that takes like a couple of hours to process even, and then I have to upload it to YouTube, and that takes a while too. So it could be later in the evening before the link to the video gets up on Blackboard, or it could be the next day as late. But the notes usually can get up really fast. That's really easy to post, right? But the video is harder because these videos are really long, and they take a long time to process.
Okay, thank you.
Yeah. and sometimes they'll crash, so I can't promise that we'll get every video perfectly right. So that's just going to be unfortunately true through the semester. All right, so let me see if I can find the notes, and I'm going to start. I'm going to start adjusting the screen. So I think that I think the camera position will be a little bit better this time than it was last time because I flipped my computer. But you'll probably be staring at the top of my head or maybe at the ceiling sometime. So that's just the way it's going to be to allow me to write on here. So what I'm going to do is switch back to the notes. Let me see if I can find the right notes here. Okay. And but before we do that, I'm going to try something new. Let's try taking, I don't know how to do this, so y'all may have to help me with this. Let's try taking a poll here in Zoom. And so I've got a couple of questions here that are kind of review questions from last time. And so I'm just a little bit curious as to how your comprehension was from last time, and just to maybe review a couple of essential things there that we went over in the lecture last time before we resume the lecture. So let me see if I can start this poll. Can y'all see those questions? Or do I have to launch polling first?
Yeah.
There's about 5 questions, but we're only going to look at the first couple of questions. So actually, I'll only get you to respond to the first question, just the first question when I launch this polling. Okay. So can y'all see that first question? It says a graph can be considered a relation because. Do y'all know how to answer do y'all have a mechanism for answering the question?
Yeah.
On your Zoom screen?
Yeah.
Because I haven't
Yes,
tried
it
this
pops
myself.
up. It pops up on the screen.
What now?
It pops up on the screen.
It pops up on the screen and you just hit a B, C, or D or something like that?
Yeah.
Yes.
Oh, okay. All right. So so try just that first question. A graph can be considered a relation because, remember last time we learned the definition for the very abstract mathematical definition of relation. And it turns out that a graph can be considered a relation. Can you remember why that was the case? So see if you can answer that question kind of quickly here. Just go with your gut instinct if you can't recall very well.
It won't let you submit unless you answer all the questions. Will you still see my answer?
Oh my God, really?
Yeah.
Okay. All right. Well, let's just talk about this then. All right. Okay. All right. And next time I'll have to break up the are y'all answering all the questions? Because some of them we haven't went over yet.
I submitted mine.
Do you want us to answer all the questions?
Well, just answer one and then submit, okay? And we can relaunch the polling. So just answer the first one and then submit. Will it let you do that?
Okay.
No, it won't let
No,
you.
it won't.
Oh, okay. All right. Well, never mind. Let's just, all right. So I'll fix this for next time, but let's just look at the first question and we'll talk about it. So a graph can be considered a relation because what do you think is the right answer there? Any suggestions from the class?
All of the above?
Yeah, all of the above.
All of the above. Okay. All right.
I thought graphs are points. Sets of
Yeah.
points.
Right. It's really number 2. Okay. So because graphs are really nothing more than sets of points, right? Okay. So I'm glad you answered all of the above because that means I did a good job of coming up with fake answers there. All right. but the right answer is really just number 2. Okay, remember, a relation is just a set of ordered pairs, right? But you can think of an ordered pair as being the coordinates for a point, and graphs are nothing more than sets of points, right? When you make a graph, all you're doing is plotting either a few points or maybe a lot of points, right? Okay, so the reason that a graph is a relation is because graph is nothing more than a big set of points. Okay, what about number 2 then? An equation in 2 variables. It's important it's in 2 variables, but an equation with 2 variables in it, like x and y, can be considered a relation y. So why can equations, also like graphs, also be considered relations? What do y'all think about that one?
Solutions to the equations are ordered pairs.
What now?
Number
Third
3.
one.
Number 3, that's right. It's number 3 is the right answer, because solutions to equations, right, are ordered pairs. If you have an equation in 2 variables and you write down a solution to that equation, that means you have to have a value for the first variable, usually x, and a value for the second variable, usually y, right? And once you have an x value and a y value, that means you have an ordered pair, okay? So a solution to an equation is just an ordered pair, right? Okay, and so all the solutions to an equation would be a big set of ordered pairs. So anytime you can, you have any sort of device that creates ordered pairs for you, like graphs or equations in 2 variables, then you're going to have a relation, okay? Because a relation is just a very simple definition, all right? Just a set of ordered pairs. All right, let's end that, okay? And next time I'll do the polling a little bit better, okay? But that was a good experiment there because that taught me something, all right? So thanks for your input. Okay, what I'm going to do now is just switch back to the, I'm going to change the share here so that we're hopefully just looking at the, notes, all right, instead of the whole screen. So is that what y'all are seeing now? Just the notes themselves on the screen?
Yeah.
Okay, all right, and then if I need to switch back to the other windows as well, we'll do that. Let me see if I can get my windows arranged better here. All right, so this was the last example that we were looking at last time, okay? And so here we had an equation in 2 variables, right? And we were discussing why exactly the answer to that polling question that we had just a moment ago there. We were discussing why the solutions to this equation could be considered a relation, right? Because this equation has many solutions. Each one of those solutions is an ordered pair. And so when you write down all the solutions to this equation, you get this big set of ordered pairs. We wrote down 3 solutions to the equation. There are a lot more solutions as well that we could write down. In fact, we could create new solutions to this equation, right? By picking a value for x, or at least a meaningful value for x, and then finding the corresponding y value. That's how we generated these solutions last time. Or you can also go vice versa. You can pick a value for y, and then by solving the equation, you can find the matching x value as well, right? Okay, and so we could, by using that process, we can generate lots of solutions to this equation. Remember, in this equation, the variables had meaning, okay? This is not just an abstract equation. Remember, in this equation, x represented the elapsed years after 1900, okay? So x variable here represented elapsed time measured in years. By elapsed, I mean measured after the year 1990, okay? And the Y here was the life expectancy for female high school dropouts in that particular year, okay? Of course, as I mentioned, you can generate lots of solutions to this equation by, again, picking different X values and solving for Y, or picking different Y values and solving for the matching X. It turns out if you generate all of the solutions to this equation, okay, and plot those ordered pairs as points on a graph, you're going to get a graph that looks like this, okay? In fact, it's going to be a straight line. There are the three solutions that I have plotted as dots here in the table. But if you generate all the solutions to this equation and plot all of them, you get a nice straight line that looks like this. So here's a graphical representation of that same relation that's defined by that equation that we give in this example. This seems like a really basic and elementary concept from algebra, right? That we can graph equations, and indeed it is. That's one of the key ideas in all of algebra, right? We can convert equations to graphs, and also we can convert graphs back to equations. But that idea is so important, especially in calculus, that I want to emphasize it. So it seems like a really a simple idea, but it's really crucial for calculus that you understand and remember this important idea, right? If you have an equation in two variables, that's a relation, okay? Because we can think of the solutions as being just a big set of ordered pairs, right? Okay, but you can graph the solutions to that equation. So you can take that equation and you can draw a picture of it, all right? Okay, and the reason that drawing pictures of equations is so useful to us is as humans, you know, we are very good at processing visual information. So it's often useful to take an idea and turn it into a picture. So if you take an equation and turn it into a picture, that's often very helpful to help you understand the relation. And that exact phenomenon happens right in this problem, right? Because when we graphed this equation last time, right, and came up with this picture, we immediately noticed, of course, that the graph is decreasing from left to right. That is, as elapsed time is increasing, as elapsed time is changing, right, the life expectancy for these female high school dropouts is also changing, correct, right? It's going down and it's decreasing. And that's important to know, right? Okay, that tells us something about the general state of health, right, for female high school dropouts, or the sort of general situation for female high school dropouts. It's getting worse, right? Okay, or it has been getting worse for the past few years, and that's information that we need to know, right? Okay, so we can figure out if we were public health officials, right, or you know, other people that were concerned with this particular population, we would need to know that so we could think about how could we improve the situation for female high school dropouts, right? What's going on with that population that's causing their life expectancy to decrease, right? Notice I worked the word change right in a couple of times into my discussion there, right? Because again, this is an important idea in calculus too, right? Remember, differential calculus, the first part of calculus is the study of change, right? When one quantity changes, in this case, right, when elapsed time changes, calculus helps us understand or analyze better how a related quantity, like in this case, life expectancy, is also changing, right? Okay, that's really the key focus of study for differential calculus. Now, if you were just looking at the equation itself, none of that I just talked about would be apparent, right? Okay, if I just gave you that equation, you wouldn't immediately see, oh yeah, life expectancy is decreasing, right? Okay, for female high school dropouts. That's not clear at all immediately from the equation, right? Okay, but when you turn that equation into a picture, then that situation becomes immediately obvious, right? Okay, so we're going to be doing that a lot, turning equations into pictures, because equations help us, pictures help us understand what's really happening in an equation, or sometimes vice versa, taking the picture and turning it back into an equation, because equations are also very useful to us as well. This is calculus and it involves algebra, and algebra is all about equations, right? So obviously there's something good about equations as well. All right, so let's take another really simple example of graphing. Okay, so you understand this really well, right? Okay, how to graph an equation. The basic process that you would teach to when do you learn how to graph equations? 10th grade maybe, or 9th grade? The basic process that you would teach a 9th grader or a 10th grader, right, for graphing equations is exactly what we discussed, in that life expectancy example, right? What we need to do is generate solutions to this equation, correct, right? And once we've got solutions to this equation, then we can plot the solutions and see the graph, right? How do we generate solutions to the equation? Well, usually you just pick a value for one of the two variables, right? See, this is an equation with two variables. So you pick a value for one of the two variables and you substitute, right, and solve for the other variable. Let me rewrite this equation though, because that process of, if I can get my pen to cooperate, there we go. That process now of, plugging a value in for one of the variables and solving for the other variable, sometimes that process is simplified if you rewrite the equation in particular ways. So what I'm going to do is solve this equation for x. So I'm going to take the x and move it to the right-hand side. So I get x equals y squared, and then I'm going to bring the 2 back over to the left. So I have y squared minus 2, okay? That's the same equation, I just rewrote it. And the reason I wrote it like this, notice I've got it solved for one of the variables, right? You have this equation solved for the variable x, is that makes it really easy now to substitute a value for y and figure out what x is going to be. So all we have to do is pick values for y and plug them in, and then immediately we'll know what x is. What value for y would y'all like to start with?
3.
3, okay. That wasn't the one I had in mind, but anyone will do, right? Okay, so when you plug 3 in for y, right? Plug 3 in for y, what does that give us there? That gives us what? 3 squared minus 2 is what x is going to be, right? And oh, that's pretty easy. Is that 7? Am I doing that right? Don't let me make an arithmetic mistake, and I will make them from time to time, right? Okay. All right. So so there's one solution when x is 7. 1, 2, 3, 4, 5, 6, 7. Y is 3, right? So this ordered pair right there is part of the graph. Of course, that's not enough to make the graph, right? Okay. So so we need to plot a few more ordered pairs, right? Y'all have any other suggestions?
0.
0 for y, yeah. Oh, I like that one. Okay. So let's let y be 0. And when y is 0, then it's really easy to see, right, that x is going to be minus 2. Is that correct, right? Just plug 0 in for y, and you get that x is going to be minus 2. So minus 2 and 0 right here is, there's another point on the graph, okay? Any other suggestions there? Let's just try a few there. So when y is 1, what do you get for x?
-1.
-1, right, okay. So when y is 1, I'm sorry, when x is minus 1 right there, y is 1, right? Okay. What about when y is minus 1? Let's not forget about negative values for y. So when we plug that in, what do we get? Be very careful when you plug minus 1 in for y, right? Because you're plugging a negative number into that equation. So I'm going to put that in parentheses. That's to help me avoid making arithmetic mistakes. So when I plug negative numbers into expressions, I like to put them in parentheses, okay? And so what do you get for X in that case? Someone help me there.
-1.
-1 again, right, okay. So when Y is -1, X is also -1, okay. Wow, what do y'all think? So if I were able to spend a lot of time here, maybe the rest of the afternoon, right? And if I were able to generate all the solutions to this equation, I really couldn't generate all the solutions to this equation, right? Okay, because that would be infinitely many solutions, right? So I couldn't have all that time. But if I were able, just theoretically, to generate all the solutions to this equation, right, and plot them, what sort of picture there y'all think this is going to turn out to be? Well, I think it's going to end up being like what?
I was going to say like a sideways parabola.
That's exactly what it is. It is a parabola, and like this. Okay, so hard for me to make really good pictures when I'm drawing on this screen, but it would look something like this. Actually, it'd be symmetric. So the top half here and the bottom half would be the same, just rotated around the x-axis. So I didn't draw a very good picture here, but indeed it is a sideways parabola. Okay, now that's kind of hard to know if you're just looking at this equation for the first time, right? What sort of picture to expect? So even if you plot a lot of points, if you don't have any prior knowledge of what the graph of that equation is supposed to look like, you are probably not going to be able to draw a really good picture. And that's one of the things now that calculus is going to help us with, is understanding what graphs of equations are going to look like, you know, when we encounter a type of equation that we haven't experienced before. Okay, so that's going to be one of the really great applications of calculus. Is it going to help us understand what graphs, what we should expect to see when we graph an equation? All right, so you guys are probably already familiar with parabolas. All right, so from your study in pre-calculus, so you probably had an idea of what the picture was going to look like, right? Okay, but in calculus, we're going to experience lots of different types of equations in two variables, and calculus will give us lots of tools for understanding what we should expect to see when we make a graph before we actually make the graph, so that we'll know that we're making it right. Let me show you why. Let me show you why that's important. Okay, because let's look at another example here. If I can get my get out of the way. If I can get some of my windows moved out here. Okay, so let's look at this next example. See, this is a more complicated equation, okay? But it's still an equation in two variables, right? Still an equation in two variables, so that means it's a relation, okay? It's just a lot more complicated equation in two variables, all right? So if we're expected to know what the graph of this one is going to look like beforehand, wow, that's going to be really tough, right? Okay, I have no idea what sort of picture I should expect to see, right, when I convert this equation to a graph, right? In other words, when I write down the ordered pairs that are part of this relation, right, and plot those ordered pairs, what sort of picture would I expect to see? If you try to do this now in just the naive approach, let me show you what can go wrong, okay? So the naive approach again, right, this is kind of the 9th or 10th grade approach, would be, well, I'm just going to plug in some different values for X, right, and find the matching Y value. So there's a bunch of ordered pairs, or vice versa. I'm going to plug in a value for Y and try to find the corresponding matching X value, right? In this case, though, notice that for this, the way this equation is written, it's already solved for y, right? You've already got it solved for y. So it's much easier just to plug in values for much easier just to plug in values for x, and then grind through the arithmetic, and you'll automatically have, right, what the matching y value is going to be. So I think that's the way that this table was generated. Just plugged in some values for x, and using the arithmetic, we found the matching y value. Let me demonstrate that one. Let me demonstrate that for you with a couple of these, like 0, 0. This one's so easy, right? So if we plug 0 in for x, we're supposed to get 0 for y. Well, that's going to be true, right? Because if you plug 0 in for x, notice that right here, you're going to be multiplying times 0, right? So you have 130 times 0 times, and it doesn't matter what turns out to be in the parentheses here when you plug 0 in for x, because when you multiply by 0, you just end up with 0, right? Okay, so it's kind of obvious there why this point 0, 0 is on the graph. So let's plot that. So that's right at the origin. 0, 0 is often referred to as the origin, right? Okay, so there's a point that's on the graph of this equation. Let's try this one also, 1, 1, just to make sure that that's really on there, because I'm not sure that I did the arithmetic right. So let's see, I'm going to plug 1 in for x. So I have 1/30 times 1 times 39 minus 10 times 1 squared plus 1 to the 4th power. So let's see if we can do that arithmetic. Look, 1 is not a negative number. So when I plugged 1 into this expression for x, I didn't bother to put the 1 in parentheses. But if I had been plugging -1 in for x, I would have put the -1 in parentheses. That's just a little bit of a safety measure to keep you from making arithmetic mistakes. So I want you to keep that in mind, right? When you plug negative numbers into expressions, try to remember to put them in parentheses in the expression. It'll help you avoid arithmetic mistakes. Let's see, is this really turned out to be 1, or did I mess this up? So I have 1/30 times 1 times, what does all this turn out to be? Let's see, that's 39 minus 10 times 1 squared is just going to be -10, right? Plus 1. And does that turn out to be 30 in there? Yeah, it does, right? So I have 1/30 times 1 times 30. And yeah, sure enough, that turns out to be 1. So indeed, this point is really is on the graph, right? So let's plot those points. So let's see, -3 down here, and -1 is right there, and then there's 0, 0, and then 1, 1. We just verified that one right, and then 3, 3 up here. What does that look like? What sort of curve does it look like you're going to get there out of that?
A line.
A line, right? Yeah, all those points fall in a straight line, right? So so it looks like we can draw a graph of that equation just by connecting those points with a straight line. That turns out to be, unfortunately, wildly incorrect, okay? So when you actually graph this equation, when you actually graph this one, here's what the picture actually looks like, okay? There's the correct graph for that equation. See, it's got a lot of wiggles in it, right? Okay, so it definitely does not turn out to be a straight line. Okay, and so that is the issue with just kind of using the naive approach to graphing, where you just plot some points and then connect the points with the curve that you think goes through those points, right? Okay, sometimes that method doesn't work. Okay, but in calculus now, we're going to learn some very important tools that will help us understand before we actually start trying to graph such an equation. Calculus can help us understand what to expect from the graph. Okay, what the graph is really going to look like. In fact, calculus can help us understand, is the graph increasing or decreasing from left to right? Okay, so what the direction of the graph is, okay? And calculus can also help us figure out where these points are on the graph. So these are the points where the graph forms, notice, peaks or valleys, and calculus can help us discover, before we actually try to make a graph, where those points are really located at. And when you have that information, then you can really make a good graph by hand. I won't say easily, but you can make an accurate graph by hand. All right. Now, however, we are in the course frequently going to rely on software to help us make graphs. So this graph was generated with a computer, okay? And obviously I didn't draw that by hand. And so we're going to use the computer a lot to help us make graphs. So if you have a graphing calculator, then that's a great tool, and you can certainly make use of it. We will also, however, I will show you software that we can use that's freely available on the web. It's a website that you can use for making nice graphs like this one, okay? And so that's really going to be an important tool for us in the course. Here's another example. So I'm not going to go through the steps of graphing this equation, but this equation was graphed with software, right? So we just relied on the software to help us generate a graph for this equation, okay? All right, so in a minute, in our last example here in these notes, I will show you that software just to show you for the first time. And eventually, though, we'll start allowing you to make use of it on your own, or again, you can use, if you have a graphing calculator, many of you have graphing calculators available to you. So you can use those, all right? Okay, let me introduce to you here a couple of more concepts that I know you're familiar with, right? And that are really useful to us, again, in calculus. So you've seen these ideas before, but they're going to recur a lot in calculus. So I want to remind you of those. Before I do that, do you guys have any questions, though, so far? All right, so again, everything should really be a review here, right? I'm just trying to hit the key concepts that we're going to exploit a lot in calculus, just to remind you of those. All right, before we get into this definition of X and Y intercept, which again, I know you know, it's pretty easy to understand. It's not a complicated definition. Let's pause here and take a breath. We've already been talking for a lot, so let's take a short break here. What I'm going to do is pause the let's pause the recording, man. I hope I don't cancel it. Okay, guys, so I've come back. So if y'all are within the sound of my voice there, I'm going to start talking again. Are y'all back?
Yes.
Yes.
All right. Okay, so so let's talk about this very easy idea of X-intercepts and Y-intercepts, because again, these play a key role in calculus. So I just want to remind you of what those are, right? So when you make a graph, right, sometimes that graph is going to cross the x-axis, not always, but sometimes it will cross the x-axis. And so that number where the graph, or sometimes you can say the point where the graph crosses the x-axis, that's called the x-intercept of the graph, right? And then we have a corresponding concept for where the graph crosses the y-axis. That number, or sometimes you can refer to it as the point, that number is called the y-intercept, right? So y-intercept, where a graph crosses the y-axis, x-intercept is where a graph crosses the x-axis. So let's look back at this equation, right, that we were constructing a graph for earlier, y squared minus x equals 2, right? And let's see if we can find the x and y intercepts. So remember, that was this graph. Scroll up here properly. That was this graph right here, right? Okay. And so I think we can actually see here on the picture, right, the x and the y intercepts. Here's the number where the, right there, right, is the number where the graph crossed the x-axis, right? at that number. And then there's a couple of places here where this graph crosses the y-axis. So X and Y intercepts are not unique, right? You might have multiple y-intercepts and you might have multiple x-intercepts as well. Okay, so it looks like this graph has one x-intercept and but two y-intercepts. Now, you can see those from the picture, right? Okay, but if you want to find those from the equation, that process, by the way, is called finding the intercepts analytically. So if you want to find information from an equation, that's called analytically. Of course, if you find information about a relation from the graph, that's called graphically, right? So we can graphically see the two y-intercepts on this graph, and we can graphically see the x-intercept. But if we want to analytically find the x and the y-intercepts, that means find them from the equation. Well, here's the process, right? To find the x-intercept, right? That is, again, where the graph crosses the x-axis. Well, points where a graph crosses the x-axis, right? If a point is sitting on the x-axis, that means the y-coordinate for that point has to be 0, right? Because along the x-axis, all of the points on the x-axis, their y-coordinates are 0, right? So to find the x-intercepts of a equation, you simply set the y to 0, right? Set the y to 0, and then you have to solve for x. Well, we already did that back earlier when we were trying to make this graph, right? Remember, when we generated this point on the graph, we set the y to 0, right? And then we solved for x. So we ended up getting, this point minus 2, 0. That's the point that we plotted right there, correct? So that is the x-intercept for this particular graph, or for this particular equation, right? Okay, minus 2 and 0. Normally, this is the number I would call the x-intercept, is minus 2. But if you want to think of the x-intercept as a point, then it's the point minus 2 and 0, right? So you find x-intercepts by substituting 0 for y, right? Okay, so remember, that's backwards, right? You find x-intercepts by plugging 0 in for y. Now, to find the y-intercepts, the process is just reversed, right? So to find the y-intercepts, since y-intercepts are where a graph crosses the y-axis, anywhere on the y-axis, the x-coordinate is 0, right? The x-coordinates for every point on the y-axis are 0. So if you want to find the y-intercept of an equation or of a graph, you do the opposite. So you set x to 0 and then find the matching y values. Let's do that in this back in this equation, right? So I'm going to set x to 0. So you get y squared minus 0 is equal to 2. And that means y squared is equal to 2, right? And when you solve this equation for y, you get y is equal to, be careful now, you're going to take the square root of both sides, right? And to solve for y, take the square root of both sides. But so y is something like the square root of 2, correct? But remember, 2 has two possible square roots. One of them is positive and one of them is negative. So the actual y-intercepts are, one of them is positive square root of 2 and the other one is the negative square root of 2. So these are those two numbers that we saw on the y-axis before. So this graph has two y-intercepts. Square root of 2 is about 1.414. And so the negative square root of 2 is about minus 1.414. Did I graph those? The top one's not too bad. The bottom one I missed a little bit when I was drawing the graph, right? Okay. So two y-intercepts, but just one x-intercept. Usually that situation is reversed. Usually you will have just one y-intercept, but you might have multiple x-intercepts. So this equation is a little bit unusual in that sense. So see, that's just a very easy definition that you already, I know that from algebra, correct, right? So remember that process of how you find x and y-intercepts. That's going to be really important to us in calculus. You will learn that very quickly because we're going to do that a lot, right? Okay, so be sure you can answer this question right. How do we analytically find? Analytically means from the equation, how do we find X and Y intercepts? And of course, what are X and Y intercepts? Well, you know that, right? Where the graph crosses the X or the Y axis, respectively. All right, let's try that on. Let's try that process on this particular equation, right? Okay, and then it says sketch the graph, but we're not going to do that by hand. We'll just see a computer-generated graph of this nice equation. All right, so again, let's start with y-intercepts first, because those are usually easier, not always, but usually. So how do I find the y-intercepts? What do we do?
Set x equal to 0.
Set x equal to 0, right? So that's so easy here, right? So we know that the y-intercept is going to be just set x equals 0 in this equation, right? So kind of boring, right? We just get that the y-intercept is going to be 0. So so that means that the point 0, 0 is going to be on this graph, right? That's the origin, by the way, of course. And see when set x to 0 and y turns out to be 0 as well. Okay, so very not exciting y-intercept, right? The graph crosses the y-axis right at the origin. Now let's see if we can find the x-intercepts. And remember, the process is just the reverse, okay? So you set y to 0 and then solve for x. And notice that turns out to now be considerably more challenging, right? Okay, because now we have to solve this equation. That's usually going to be the case for us in calculus. The y-intercepts will be easy to find, and the x-intercepts are going to be a lot more challenging to find. Unfortunately, in calculus, the x-intercepts are more useful to us usually than the y-intercepts. So we're going to be more interested in finding the x-intercepts for lots of reasons, but the x-intercepts are harder to find, okay? So the thing we want the most is the hardest to find. That's true in life, usually, right? Okay, well, definitely true in calculus as well. All right, so do y'all know how to solve this equation? Any suggestions for solving this equation? Other than just guessing? We don't want to guess, right?
You can factor. Wait, are you trying to solve for x or y?
Well, there's no y in this equation, right? Because I plugged 0 in for y, right? So the y is gone, so I have to solve for x, right? This is no longer an equation in 2 variables, right? The original equation was in 2 variables, but this is now just an equation in 1 variable. So x is the only thing I can solve for, right? Yeah. So what did you say? Try there.
You can factor out an x.
Factor. Yeah, that is, oh darn, I lost something there. Okay, so lost the chat window. That's exactly a very good suggestion. We want to factor, okay? So, explain to me there how to factor that. Is it Jocelyn? Is that who was talking?
Sorry?
I just trying to call you by name, but I don't know who
No,
was.
that's not me.
It was
okay.
me, Donna.
Well, so who's talking?
Donna.
Donna. All right. So Donna, how do we factor here?
So the only common term between them is 1x. So you can take 1x and then put x squared minus 4 in parentheses.
Love it. Yeah, you did that beautifully. So factor out the common factor, and you want to factor completely, Donna. So can you do any more factoring here?
Yeah, I think I'm not sure exactly what it's called, the x squared minus 4, but it becomes x minus 2x plus 2.
Yeah, that's perfect. That's called difference of 2 squares. So the reason that's called difference of 2 squares is, notice x squared is a perfect square, right? It's obviously x squared, and 4 is also a perfect square because its square root is 2. So, and this is the difference of those 2 perfect squares, right? Because you're subtracting. And so remember, when you have difference of 2 squares, That's one of the very first factoring patterns you learn in algebra, right? That's going to factor as the difference of the two square roots and then the sum of the two square roots. So x squared minus 4 factors as x minus 2 times x plus 2. Now, Donna, why is it that the factoring was useful to us in solving the equation? I mean, it's kind of fun to do that algebraically, but you know, why do we care about that? Why does it help us solve the equation?
I'm actually not 100% sure.
Mm-hmm.
But now, actually, because okay, so if one side is equal to 0, then one of the pair of parentheses or something has to also equal to 0.
Yeah,
So
you said that almost perfectly right. Okay.
Yeah.
Notice that when we factor an expression, what factoring means is you take an expression and you write it as a product. Okay. Remember, products are formed from factors. So when we factor an expression, that means we write it as a product. So here we have the original x cubed minus 4x written as a product, right? It's x times x minus 2 times x plus 2. And in arithmetic, this is not even algebra. In arithmetic, you learn way back in, I don't know, 4th grade or something. When you have a product that equals 0, the only way that can happen is if one of the factors is 0, right? When you multiply numbers together and you get 0, the only way that happens is if one of the numbers is 0. So you know that x is 0. That's a possibility, or x minus 2 is 0, or x plus 2 is 0. That's why factoring is so useful in solving equations, okay? But these equations are really easy to solve, right? This one's already solved. It's x equals 0, right? What's the solution here, of course? X is going to be what?
2.
2. And here, the solution is equally easy. It's going to be x equals minus 2, right? Okay, so there are your 3. You have 3 of them. Wow, we have just a real treasure here, trove of x-intercepts. 0 is 1, 2 is 1, and minus 2 is also an x-intercept. So when we make a graph of this equation, when we convert this into a graph, it's going to cross the x-axis 3 times. That already tells us important things about the graph. For instance, we know it's not a straight line, right? Okay, because if it's a straight line, it's not going to wiggle enough to cross the x-axis 3 times, right? So we know that this graph has to have some wiggles in it, so it's not a straight line. That's already important information about a graph, not a straight line, okay? All right, well, here's what it actually does look like, okay? So I generated this again with graphing software, right? And you get this nice, pretty curve, right? Okay, and see, there it is, crossing the x-axis at minus 2, and then at 0, and then again at 2, right? Now that's, knowledge of the x-intercepts is not enough to help us, make the graph, right? But it's certainly a start, correct? Okay, in helping us, at least when we draw the graph with the computer, right, we can understand, oh yeah, this may be the right graph because it's got the right x-intercepts, right? It's got some other interesting features on it as well. It's got a peak point right here, and it's got a valley point right there, okay? Those are other points on the graph that we would like to be able to discover as well. What's that peak point, and what is that valley point? And that's one thing that calculus is going to help us determine, okay, where this peak point is located and where this valley point here is located, okay? All right, so there's just a really quick example of finding x and y intercepts. By the way, just to give you a little bit of a preview here, this peak and this valley point, you might think that has nothing to do with x-intercepts, but it turns out that finding the peak and valley points is really the same as finding x-intercepts. So that's kind of strange why that's the case. That's one thing that we're going to discover with calculus, okay? All right, let's look at another problem here. that is also kind of similar to finding X and Y intercepts, but also is an important problem in calculus, okay? All right, so this problem says find the points where the graphs of these two equations intersect, okay? And that means cross, all right? So, you know, when you find the X-intercepts, right, you're finding where the graph crosses the X-axis, or when you find the Y-intercepts, you're finding where the graph crosses the Y-axis. So this is a little bit more general question. We have two curves, but neither one of them is the X or Y axis, but we want to figure out where these two curves, the graphs of these two equations, those are going to be curves. We want to figure out where they cross each other, okay? So at what points, if any, maybe they don't cross each other at all, they don't have to cross each other, right? But where would these two graphs cross? All right, let's actually, I'm actually now going to show you, I'm actually now going to show you a little bit about graphing these, okay? And so I'm going to switch to some graphing software, and I'm going to show you how to graph these in the, or show you them graphed in the graphing software. One thing I'm going to do before I show you that, though, is let's rewrite both of the equations first. I'm going to take these two equations and I'm going to solve them for, I'm going to take these two equations and I'm going to solve them for y, all right? So what I mean is I want to write the equation in the form y equal to some expression, all right? That's what I mean by solving the equation for y. And you can do that pretty easily in both equations just by moving terms around from one side of the equation to the other. So I'm going to take the minus y term that's on the left-hand side of this equation, and I'm going to move it to the right. And then I'm going to take the 3 that's on the right-hand side, and I'm going to move it back to the left. Remember, when you're moving terms from one side of the equation to another, you can do that really easily. You just have to remember to change the signs. So when I rewrite that first equation, I get x squared minus 3, because I'm moving the 3 to the left-hand side, is equal to positive y, because I'm moving y to the right-hand side. And I'm going to interchange both sides of this equation. I'm going to write this as y equal x squared minus 3 instead of x squared minus 3 equals y. That's the same equation, right? Same thing for this equation. I'm going to shift terms around. So when I shift the minus y to the right and the 1 to the left, I get y equals x minus 1. And now I'm going to transpose both sides of the equation. So I'm going to write the y on the left and the x minus 1 on the right, but that's really the same equation. So I'm getting them in the form y equal to some expression for the first equation, in the same form for the second equation, y equal to x minus 1. That makes it easier for me to graph. All right, so let me change here my share. Let's go back to the screen. And so here's the graphing software that I'm using. This graphing software is called Desmos, and we'll practice Desmos more throughout the course. This is just kind of our first shot here at Desmos. So can y'all see Desmos there?
Yeah, we see this.
Yeah, okay, because I was trying to show the whole screen. So, all right. So so Desmos is pretty easy to use. I'll tell you what the web address is, although you can find it just by Googling Desmos. So when you go to Desmos, you just see this, this rectangular coordinate system, right? This Cartesian coordinate system. And all you have to do here on the left-hand side is just type in the equation that you want to graph. So, and it's easier to type it in the form y equals to some expression, right? So that's why I rewrote the equations. So let's see if we can do that. So y, let's not make it caps here. So y, and then let me see if I can find an equal mark. Equals, and then there's the x, right? Let me see if I can and by using the caret key, the caret key there, I can get squared. And what was that first? What was that first equation? Y equals x squared. Was it -3?
Yeah, -3.
Yeah. Okay. So there's y equal x squared -3. See what a beautiful graph that makes there, right? Okay. Such a nice graph. See, just easy. Just type in the equation, and to get the superscript there, the exponent of 2, I just hit the caret key, and it gave me the exponent. Notice Desmos so friendly there. It plots for me it plotted the 2 X-intercepts, right? So there's the decimal approximation for X-intercept on the right, 1.732, and then on the left, -1.732, right? Is the X-intercept on the left, and of course there's the Y-intercept, which is down here at -3. All right. Now I'm just going to click right here, and it'll allow me to enter a second equation, and it'll graph it on the same set of axes. So let's see, what was the second equation? Y equals something or other. What was it?
Y equals x -1.
Y equals x -1. Okay. So there's the second equation, graphed it in a nice different color for me, right? Okay. So notice that's just a straight line, right? Y equals x -1 is just a straight line, and see the graphs do cross each other, right? Okay. And Desmos was really friendly again. I didn't know it was going to be this friendly. It actually shows me here the 2 intersection points. These are where the 2 graphs cross each other. So one of them there is at 2, 1, right? And then another one here at -1, -2. All right. So just by making the graphs there of these 2 equations, see, we can find those 2 intersection points. So finding the 2 intersection points by looking at the 2 graphs, that's called graphically finding the intersection points, right? You're using the graph to find the 2 intersection points. Okay. I think I have another picture. Let me switch back here to our notes. I think I have another picture there of this. If I can get this out of my way. Let me scroll down in the notes here. I think I include, yeah, there's the same picture I already pasted there into the notes. So when you're looking at the notes there, you'll see the 2 intersection points, right? Again, this was at 2, 1, and then the other one here was at -1 and -2. So we can find those 2 intersection points graphically, right? Okay. All right. Now, however, suppose we want to find the 2 intersection points simultaneously. Okay. So any suggestion? I'm sorry. Suppose we want to find the 2 intersection points analytically. All right. Because that's the instruction here that's given, or that's the question that's asked here with the problem. How do we analytically find where those 2 curves intersect? So analytically means we would just be using the equations. So we wouldn't be looking at the graph, but just looking at the equations. How can we find those 2 intersection points? Any suggestions for how to do that?
So I'm not sure about the first step, but I think you're supposed to move everything to one side of the equal sign and then make the 2 equations equal to each other.
Yeah, I'm not sure what you said first, but the second part is correct. You want to make the 2 equations equal to each other. All right. So what do I mean by make the two equations equal to each other? Okay, because that's kind of a that's not quite clear what we mean, right? How to make two, we know how to, set two numbers equal to each other, right? Or two expressions equal to each other, but how do you say two equations are equal to each other? Well, here's the idea, okay? Notice in this first equation, after I had it solved for y, right? That first equation tells you that y is equal to x squared minus 3. So whatever x is, y is going to be that squared minus 3, right? Okay. And the second equation tells you that y is equal to x minus 1, right? Okay. So notice both of these equations say y equals, right? So what I'm going to do is, since in the first equation, y is equal to x squared minus 3, I'm going to take the expression x squared minus 3, and I'm going to substitute it for y in the second equation, right? Okay, because see, that first equation tells me whatever y or whatever x is, y is going to be that squared minus 3, right? But that second equation also involves y, so I can take this expression and substitute it for y in the second equation, right? Because this is what y is equal to, right? According to the first equation. So when you do that, notice what happens. So on the left-hand side here, instead of writing y, I'm going to write x squared minus 3. Well, when you do that, see, notice what happens. You end up with an equation, but how many variables do you have in this equation? How many different variables do we have in the equation? See, this equation had x and y, so that's two different variables. But how many variables do we have in this equation now? Someone?
So now we can actually solve for the x.
That's right, because you just have one variable, right? Okay, you just have one variable x, right? It occurs twice, but the x is the only single variable. So you can solve this equation for x. Let's see now, how shall I do that? Well, I'm going to try my factoring technique again. So I'm going to set the equation to 0. So let's take the x here and pull it to the left. So that will be now minus x on the left. And let's take the minus 1 and also pull that to the left. So that will become, along with the minus 3, you'll get a plus 1 here, right? So we have x squared minus x minus 2 is equal to 0. And now we will factor, okay? So just like we tried before, we're going to factor. Let's see if we can factor this. So, how does that factor? That's not difference of two squares, but we can still factor that using parentheses. So any suggestions there on what should go in the parentheses? How do we get x squared? What has to go in these parentheses to give you x squared when you multiply the parentheses back together again?
X.
X, right. So you have to have x and x. And you also now have to have numbers here so that when you multiply them together, you get minus 2, correct? So how do you write 2 as a product? There's not many ways to write 2 as a product.
1 and 2.
1 and 2, right? 2 is a prime number. So the only way you can write 2 as a product is 1 times itself. Now all I have to do is insert the signs, okay? And if I insert the signs in the correct way, then I think I'll get the factorization correct. Since this is -2, that means one's got to be plus and one's got to be minus. So let me write the plus first and the minus second. Is that correct? When you multiply these back together, do you get x squared minus x minus 2? I think so, right? X times x is x squared, plus 1 times minus 2 is minus 2. And then for the middle term, you get x minus 2, which is minus 2x, but then you have a plus x added in, right? When you multiply these two terms together, 1 times x. So minus 2x plus x is minus x. Yay, so I got that factored correctly. And once you get it factored, you're in business. Because when you have a product that equals 0, that means one of the factors is 0. So x plus 1 is 0 or x minus 2 is 0. And now these equations are very easy to solve. You get what? X equals minus 1 or x equals 2. So what that tells me is these curves are going to intersect at 2 points, one of them with x coordinate -1 and the other with x coordinate 2. How do you find the y coordinate now of these 2 points?
Solve for y.
Solve for y, where?
Back at the original.
That's right, back in one of, and you can use either one that you like because the curves intersect here, right? So you can use either one of the equations that you like. The second one is easy to do arithmetic with, so let's use that one. When you plug -1 in here for x, you get -1 -1, which is -2, right? And when you plug 2 in for x, you get 2 - 1, which is 1. So there analytically, right, are the 2 intersection points. So we found those. Are they the same ones I got here? Yeah, good thing, right? Otherwise, something was off, right? So there's how we analytically found the 2 intersection points, right? Okay. Set the equations equal to one another, right? And solve for the variable, okay? All right, so we really understand this process pretty well, right? Well, only one example, so that takes practice, but at least we understand the idea behind the process, right? Of how to find where two graphs are going to cross each other. All right, let's quickly see if we can. I think I've got. Do I have another example here? Oh no, I don't. Okay, so let's finish here with we got a few minutes, so let's have y'all do this. All right, so I'm going to give y'all a problem to practice on, right? So if you're there, here's a problem for you to do. Okay, so if you knew how to do this really well and the lecture was boring you, well, here's a chance for you to do a little bit of practice here, right? So and I'll try to work in more examples as we go through the class to keep you y'all a lot busier, so I'm not talking so much. But here's what I want you to do: find the points where these two curves intersect. So you don't have to graph them. We just want to do this analytically, right? Find where these two curves when we graph them, but we're not going to make the graphs, right? Find where these two curves intersect, right? So find the points where those two curves intersect, right? So go through that process again, right? That we went through with this example to find where those two curves intersect. Let me write those down up here. So it's y equal 2x minus 5 and y equals 3x plus 6, right? The reason I wrote them up there is, let me scroll up so y'all can see, y'all can remember what we just did in this prior example, right? There's what we just did, and there's what we just did in the prior example, all right? So is everybody working on that?
Yeah.
Let's take about 3 minutes. So 3 minutes, and then I'm going to pull a dirty trick on you. I'm going to call on someone, okay? And you can either chat the answer to me, or you can just tell me what the answer is, okay? All right, so everyone try to get the answer there. If you get hung up, that's fine. If I call on you, we'll just go through the process together, okay? All right, so take a couple of minutes to try that.
Which one are we stopping for again?
These two right here, y equal 2x
Okay.
minus 5 and y equal 3x plus 6, right? So where would those two curves, whatever those curves look like, where would those two curves cross one another? By the way, they don't have to cross, so it is possible to get no solution here, but that's not going to happen in this case. So take about another minute. See if you can get it done in another minute.
Professor,
Hmm.
on either of the equation, is there a square on by any chance?
No, you just have y equal 2x minus 5 and y equal 3x plus 6. So no square roots, no squares, nothing like that. So that makes it hopefully makes it a little bit easier, right? Okay, so before we run out of time here, let's finish this one. So Saad, since you asked that question, let me. Did you come up with an answer, Mr.
So I
Murat?
followed the same process as you.
So what was that process?
the-
Just describe it to me.
So I took both of the equations, since
Mhm.
they're both y equals to each
Mhm.
other. So I put
Mhm.
2x minus 5 equals to 3x plus 6.
Yeah,
And
so
then
2x
I-
minus 5 equals 3x plus 6, like this, right?
That's
And
right.
then what did you do?
And then I move all the x to the left. And so I minus 3x
So you had
to both sides.
2x minus 3x equals what?
Negative x on the left.
Uh-huh. Negative
Right.
x.
And on the right side, I got I added 5 from the right side. Added 5 to both sides, so that
Right.
gives
So you
me
got
9.
Yeah, so you got 6 plus 5. So
That's
you
right.
got minus x equals what?
9.
11? Huh?
Oh, sorry, 11. Yeah, that's
11,
right.
right. Okay.
Yeah.
So if
So
minus
x
x
is equals to negative 11.
perfect. Yeah, that's right. So there's the x coordinate, Assad. That's the x coordinate of where they cross. So you know the x coordinate is minus 11. So these only cross in one place, apparently. And the x coordinate is minus 11. So how do you find the y coordinate?
You could plug it into any of the equation. So
Yeah,
if
into
you
any
add,
of those, right? So if you put it
that's
in
right.
this one, can we do that arithmetic? Let's see. We have 2 times minus 11. That's minus 22. Minus 5 is that minus 27? Yeah, right. Okay.
Mhm.
So there is the intersection point there, right? Is that what other people got? Minus 11, minus 27? We got confirmation there? Did we do that right? Can I get an agreement?
Yes.
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 Okay, right. Yeah, I need some confirmation that that's the right answer there. All right, let's wait. Let me go back to let's quickly here go back to Desmos and let's put those two equations in there. Can you so y'all can see Desmos here?
Yeah, we can.
Yes, sir.
All right, so if I can find my keyboard. All right, so that first one was what? Y equals 3x, right? 3x something. What was it?
3x plus 6.
3x plus 6. So 3x plus 6, and then the second one there was y equals, it was 2x, right? Minus 5.
That's right.
So 2x minus 5. And so there's the graphs that Desmos makes there. Notice you cannot see here the intersection point, right? By the way, notice these are 2 straight lines, right? And you can't see the intersection point, but that makes sense, right? Because we already know that the intersection point was way, way, way down here, right? Okay, so let's scroll here. I'm just dragging across the screen here, and there it is. There's our intersection point, right? And well, Desmos says the same thing, right? It says the intersection point there was at -11 and -11 and -27, right? See, there's one of the issues, that, right, with graphical solutions, right, is that you know, you make the graphs and you can't see the intersection point, right? So you know, you might get confused about where the intersection point really is, but analytically we were able to pretty easily find that, right? We know it's at -11 and 27. Okay, guys, so well, we've run out of time, so I need to stop here. And so we had a great session today. So remember, you've got that very easy first homework that's due next time, just on entering WebAssign answers. So that should be a pretty easy high grade for everyone. If you have any questions, again, email me. I will have office hours today though, right? So I have office hours from 1:30 to 2:30. So it's at the same location. So if you need to talk to me, you can just zoom in to that same ID number, right? That we're using for the lecture. All right, so we're done. So y'all can sign off now. I'm going to stop the recording. Someone was going to talk to me after class, so you can hang around, all right, and we'll see if we can get you on to whoever that was, Mr. Orozco, right? See if we can get you on to WebAssign. Okay.